Today we're going to be looking at properties of systems and their solutions. And we're going to be looking at another way of solving systems of equations algebraically. So first we're going to be looking at the solution with this system here where we know the solution is 1, 5. It's always nice when you know the answer to start. So let's prove it. So we're going to substitute in works for the first equation and works for the second. All right, so we've justified, we've shown, we've proven that this is a solution. All right, now it wants me to find the sum of the two equations. So what we're going to do is we're going to take 4x plus 2y equals 14, and then x minus y equals -4. And I'm going to add these together. So I'm going to combine like terms. So 4x plus x is going to be 5x. 2y plus a -y is going to be y. And then 14 plus a -4 is going to be 10. So what I did is I just combined my like terms straight down. Now I want to know, is this solution to the previous system also a solution to my new equation? So let's check. So is 5 times 1 plus 5 a solution? All right, so yes. The point 1, 5 is a solution to the new equation. But that doesn't really help me, because if I didn't know the solution, I still wouldn't know the solution if I was just given the system. All right, well, let's try this next one. Now it says multiply both sides of the second equation by 2 to get an equivalent equation. So basically, this is very similar to when you found equivalent fractions and equivalent ratios, right? As long as you multiply everything by the same factor, then the relationship remains true. So what I'm going to do is I'm going to multiply the entire equation and distribute everything. So I'll get 2x minus 2y equals -8. So I just multiplied every term by a factor of 2. So now I want to see, is the point still a solution? All right, so let's try this. So if I have 2 times 1 minus 2 times 5, is that going to give me -8? Yes. So yes, the point 1, 5 is a solution. Cool. So now what we're going to do is we're going to take our new equation that we found right here, okay, and we're going to add it to the first equation. So I'm going to have 4x plus 2y equals 14, and then I'm going to use my new equation, and I'm going to add it together. So 4x plus 2x is 6x. 2y plus -2y gives me 0. 14 plus -8 is 6. 6x equals 6. X equals 1. So what happened? Well, when I added them together, the y variable was eliminated. Right? When I added these two equations together, my y variable was eliminated. It allowed me now to solve for x, and I got that x is 1, right? I showed it right here. Now I know x, can I find y? Yes, I can take that and substitute it back into one of my original equations. Now the important part here is that I'm always going to go back to one of my original ones. The reason being, what if I forgot to distribute, or I distributed incorrectly, or made an arithmetic error? It's always best to check with your original work. So if I have 4 times 1 plus 2y equals 14, I still get that y is 5. And now I'm going to check 1 and 5, I know, is a solution to my original equation because I checked it right here. So I was able to algebraically show, by following the rules of arithmetic, figure out what my variables represented. So the solution to a system remains a solution if you use properties of equality to rewrite one or both of the equations. All right, and then you can add or subtract the equations, or rewrite them and add them and subtract them. So as long as you're following the properties of equality, it's okay. So let's look here. So show that the point is a solution. So we're going to go ahead and substitute that in. All right, that's a solution. Try my next one. All right, so this is a solution. The point 3, -1 will be a solution to the system shown below. How can you determine this without substituting the point in? If I look at this first equation, 8x minus 6y equals 30, and I compare it here to 4x minus 3y equals 15. If I take the first equation and multiply everything times 2, right? And I'll show that right here because I have a little extra room. So if I multiply by 2, distribute to all of them, I get 8x minus 6y equals 30. This equation, 9x plus 6y equals 21, was obtained by multiplying the second equation by 3. Okay. If we add these two equations together, so 8x minus 6y equals 30, 9x plus 6y equals 21, 17x, 0y. So you see how I was again able to eliminate one of my variables. And I was able to solve for x, and I can use that to find y. Now I'm going to go back to my original equations now. Once I solve, I'm going back to the original, just in case. So often, students don't do that, and then you've made a mistake and you don't catch it until the very end. Now I will check with my final equation. Here, 3 and -1, I put it in there, 3 and -1 is a solution. So this method is called elimination because we are eliminating one of the variables And we need to think about how we can do that here. We can do that two different ways. We can either multiply the first equation by 3, and I get 6x plus 12y equals 6. And then I have my second equation here, 6x plus 3y equals -3. And then I'm going to subtract. I get 0x plus 9y equals 9, y equals 1. Or I could multiply both of my equations to eliminate the y variable. It doesn't matter. As long as what you're doing to every term and you're keeping it consistent. You could also multiply, instead of by 3, you could multiply by -3. If I do that, then I can add. So here, multiplying by the positive, okay, my coefficients were the same, and I subtract. Here they're the opposite, and so I can add. I still get y equals 1. So you can make a little side note. If the coefficients are the same, subtract. If the coefficients are opposites, add. If they are neither of those, multiply one or both equations to make them the same or opposite. Okay. So that's how you can use the elimination method to solve systems of equations.